Hi everyone, I'm James Larish, PhD student at Harvard University. In this presentation, I will describe how many TLS root certificate stores in the web public key infrastructure lack the precision required to deal with modern certificate authority problems. I will then present some preliminary solutions for bringing all root stores up to speed. So I'm first going to provide background on root certificate stores and why they are important. We will then examine a real incident involving a root certificate, which will illustrate our central problem with root stores. And I will then describe the solution before teasing some exciting future work. First, some background. Root certificate stores anchor our security when we browse the web. To show you what that means, say you make an HTTPS request to example.com using Mozilla Firefox, which means you're using Transport Layer Security, or TLS. Example.com sends Firefox an X509 leaf certificate containing a public key that Firefox uses to encrypt communications between you and example.com. But before starting the connection, Firefox verifies that you are speaking to the real example.com by checking if the leaf has been signed by one of a few special certificates that Firefox already knows about and trusts, called a root certificate. Firefox's collection of special certificates is called a root store. If the leaf has been so signed, Firefox allows the connection. If not, Firefox rejects the leaf and tells you that you may be talking to an imposter posing as example.com. Note this is a gross simplification. Typically there are intermediate certificates in between the leaf and the root, and Firefox checks many more things beyond just the signature. Now consider the same situation, except use curl. Curl performs the same request, but uses the OpenSSL library to validate certificates, which, unlike Firefox, does not manage its own root certificate store. It uses the operating systems, in this case Debian's. To see why root store security is important, consider that Firefox and curl on Debian will happily accept any leaf certificate signed by a root that they trust. For instance, say a root is compromised and signs a leaf for google.com without Google's authorization. An attacker can use that leaf to intercept your traffic to google.com. As a result, root store operators must be careful about adding certificates to their root store, and they must monitor existing root certificate authorities for bad behavior. Because unfortunately, in practice, root certificate authorities do misbehave, either on purpose or due to negligence. For instance, imagine we're back in 2013. The French government agency ANSI, which is a root certificate authority, transitively issues a new leaf certificate for Google domains without Google's authorization. Now, Mozilla could punish ANSI by removing their root, which would cause Firefox to reject this Google certificate. But instead, they took a nuanced approach. They implemented partial distrust of the ANSI root by adding this function to Firefox. Now, whenever Firefox encounters a leaf certificate signed by the ANSI root, it calls this function, which ensures that the domains in the leaf certificate use French top-level domains. Why is this valuable? It means that as far as Firefox is concerned, the ANSI root can issue leaves for French domains, but not for arbitrary domains like google.com. So Firefox users are now safer. But what about curl users? Recall that curl, through OpenSSL, uses Debian's root store. But Debian is what Ma et al. Call a derivative root store. They mimic decisions made by a primary root store, Mozilla, because Mozilla actively monitors CA misbehavior. So Debian sees Mozilla's reaction to the ANSI situation. Assuming this ANSI root is in Debian's root store, what should they do? If they leave the ANSI root in the root store, libraries like OpenSSL will validate the fraudulent Google cert, exposing you, the curl user, to attacks. On the other hand, if they remove it entirely, this will block certificates for the .fr domain that Firefox allows. This ANSI situation is just one example. In the paper, we list 6 similar situations that have occurred over the last 10 years. This brings us to our main thesis. Derivative root stores like Debian can only express binary trust. Either a certificate is trusted or it is not. In contrast, primary root stores like Mozilla can implement more precise partial distrust of root certificates. One reason for this is Firefox has a unique advantage. It is both a TLS client and a root store. It can execute root-specific functions during validation. Derivative root stores are just collections of certificates. They cannot execute special functions like ANSIs in Firefox. The consequence of this lack of precision is denial of service at best and severe security vulnerabilities at worst. I'm now going to describe some ideas we have on how to solve this imprecision problem. We posit that partial distrust functions, like this one, embedded in Firefox, need to be standardized and distributed to all root stores, such that when an upstream primary root store, like Mozilla, implements partial distrust, derivative root stores can easily mimic such decisions. In particular, we propose general certificate constraints. A GCC is a program attached to a particular root certificate via that certificate's hash. GCCs are executed when an attached root is encountered during chain validation. If a GCC returns false, the validation of that chain fails. We also propose using a logic programming language like Datalog to express GCCs, though other languages would work too. This is a Datalog rule that all GCCs define called valid. I'll show you how to read this particular rule. We start upside down. First, get the domains the leaf certificate is valid for. For each domain, if it ends with .fr, the valid rule holds and the chain should be accepted. So, when an ANSI situation occurs, Firefox writes this GCC, and to execute it, they convert all certificate metadata into Datalog statements, like turning the subject alternative names field into the corresponding Datalog fact, shown here. They then pass these statements plus this rule into a Datalog engine. They then execute the query valid ? To check whether the GCC holds or not. If so, it accepts the chain. Under this new model, derivative root stores like Debian would also receive and execute this GCC, which brings us to one of the open challenges with GCCs that requires further investigation. For derivative root stores, who should execute GCCs? In the paper, we present three options for deployment. In the first deployment option, the client or client library pulls all roots and GCCs from the operating system and executes them during chain validation. Unfortunately, this requires each client to implement a correct Datalog engine. But in the second option, the client tells the platform which roots are being considered, and the platform executes GCCs. Now, only platforms, not libraries, need to implement a Datalog engine. But this requires significant interface changes and potentially untenable IPC overhead for every TLS connection. In the third option, we push all certificate validation, including GCC execution, into the platform. This simplifies clients significantly, but requires a new trust daemon for operating systems that can perform full certificate chain validation. We propose leveraging our existing work, Hammurabi, to accomplish this. Fortunately, no matter which path is taken, GCCs can be deployed incrementally, since derivative root stores that don't support GCCs are no worse off than they are today. That concludes our proposal for bringing precision to every root store in the web today. I'm mostly going to stop here, but I will briefly mention two other interesting things we talk about in the paper. First, we discuss how, as pointed out by Ma et al., derivative root stores are often out of date relative to their primary. For instance, if Firefox removes a root, Debian might not remove that certificate for a few months, which can lead to vulnerabilities for users of, say, curl. To address this, in the paper we propose a mechanism for primary root stores to securely distribute routine certificate additions and removals and GCCs to derivative root stores. To present our second idea for future work, we recall the 2013 ANSI incident. Let's roll back the clocks to 2012. What if, before the ANSI root misbehaved, Mozilla noticed that the root only ever issues leaf certificates for .fr domains? Now it develops and issues the same GCC as before, but does so preemptively. the root can no longer issue arbitrary certificates. We call these preemptive GCCs. Now, if a root is compromised, the fallout is limited. If this sounds familiar to you, that's because it already exists. There's an optional field called name constraints that allows CAs to constrain the domains certificates can be issued for. But as we show in the paper, it has a few problems. One of them is that almost no CAs use it. Only 6 out of 140 root CAs included by Mozilla ever use name constraints. Furthermore, preemptive GCCs allow clients, not just CAs, to constrain any field in certificates, such as their lifetime, not just names. We discussed the idea of preemptive GCCs further in the paper. Thank you very much.